This video is sponsored by PCBWay. Welcome everyone. In this video I revisit one of my older projects. This project is an automated reflow hotplate, and I've been using this device for more than 2 years without any issues. But I wanted to polish the software a little bit, and I also received some parts recently that I wanted to incorporate in the system. There's nothing wrong with the current system in its current form, maybe except that its surface area could be a bit larger. But this is one of the things that I'm going to tackle in this video, so that will be solved. I made the circuit relatively reproducible, so it is mainly consists of off-the-shelf components and through-hole parts. I received a few comments that due to the size of the board, the PCB is more expensive, which is true if you are used to the usual $5 for 5 PCBs. However, a fully assembled board still costs less than $20, which is, I think, a very good price. So coming back to the board, we have a 120 x 160 pixels display. This shows all the relevant information, including a fancy adjustable reflow curve and a real-time graph of the reflow process. We have a rotary encoder with a button for easy navigation on the display. We have an Arduino Nano for controlling the whole system. We have a K-type thermocouple module to measure the temperature of the hot plate. This will give a feedback to the controlling algorithm. Then, on the high voltage side, we have a small power supply block that supplies the 5-volt rail from the mains power. So this supplies power to the Arduino and the display and the other modules which are run from 5 volts. And then we have a TRIAC that switches the power of the hot plate. And this would not be possible without an optocoupler, so we also have an optocoupler that allows the Arduino to switch the TRIAC on or off. And also there is a power transistor that switches the 2 miniature 5-volt fans that cool the hot plate. And since these are electrical motors, just to be safe I added a flyback diode and a capacitor, so that should protect the rest of the circuit when the fans are switched. So if you want to get this PCB and build this board yourself, please visit my PCBWay project page where you can find this PCB. Or if you have your own project that involves PCBs, 3D printing or metalworking, consider using PCBWay services. If you have an extraordinary idea that involves PCBs or electronics in general, I also recommend you to check out their challenge where you can upload your project and compete for valuable prizes. So check out PCBWay's website and use their services and join their challenge. So when we look at the main screen of the reflow system, a predefined reflow curve is shown to us, and I actually took one of my solder paste's reflow curve and used it as the default curve in this system. The curve is divided into 5 parts: a preheat, a soak, a reflow, a hold, and a cooling section. Each phase, except the cooling, has an adjustable time and an adjustable temperature parameter. When an item is highlighted with a yellow color, we can press the button of the rotary encoder to enter into adjusting mode, and we can adjust the value. And then by pressing the start button, we start the reflow process. However, let's proceed further, because the fun stuff is on the next page. This page did not exist in the previous version, I added it now. The top bar displays the current temperature measured by the thermocouple, and there are 3 adjustable parameters. We can set a target temperature by selecting the number and rotating the encoder, and this temperature becomes the target temperature for the free heating. And then, of course, we can turn the free heating on or off with the heating button, and then the microcontroller will try to reach and maintain the target temperature. We can turn the cooling on or off. This just simply turns the fans on or off. This can be useful when the reflow has finished and you quickly want to start cooling down your board, for example, to solidify the molten solder. And this cooling doesn't have any target temperature, of course, so this just runs the fans. For fun, let's just start the heater. I also attached an external thermocouple-based thermometer to the surface of the hot plate to see how the temperature evolves. The heating goes well, although it has issues maintaining the target because my parameters need some further tuning. I have a proportional control developed for this board, but the parameter is not perfect yet. But that is an easier task than developing the whole system, so I'm not worried about it just now. So now I already showed some software related updates, which are the free heating and the free cooling options. But there is a literally bigger update. I managed to find a relatively cheap and high performance heating plate, similar to the one which is currently in the system. This plate cost me roughly $15, so it's not so bad. The one in the system is 10 by 15 centimeters large, and this new one is 15 by 15 centimeters. So we gained an extra 50 square centimeter area. I used the same approach as I used for the current smaller plate, and I clamp a 2mm aluminum plate on the mica heater using some metal paper clips. And actually this is more important than it initially looks, because during heating the mica heater suffers from severe swelling. This is due to the fact that the mica heater itself is wrapped with a stainless steel jacket, and then this stainless steel can expand quite significantly at higher temperatures, but the jacket is restricted in motion, so the only way for it to expand is by buckling. And then, because of this buckling, the wall package swells up. And this would be disadvantageous if we would just directly put the PCB on top of the mica heater, because at elevated temperatures the contact area would decrease and the heating would become worse. Because of course, if your PCB sits on a curved surface, then some of the areas don't touch the heater's surface properly, and then the heat transfer is much worse. So it can be that if you have a considerably large PCB on the surface of this heater, you would not melt the solder across your PCB equally. So one patch would be cold and the other patch would be warm, and you might even damage your components by overheating one part of the PCB while the other hasn't even melted yet. So this is why I clamped a rigid aluminum plate on the top of the heater. It provides mechanical support and it is relatively a good thermal conductor, so it does not really affect the heating too much in a negative way. I also added a little gadget to the circuit. I recently bought some neon light bulbs which can be used as mains power indicators. I added one to the output terminal of the TRIAC, so when the hot plate is powered, I can see it. Of course, the microcontroller should tell me the status of the heater, because that's what I control, but what if it doesn't work? So this is an extra layer of safety, so I know that the light bulb is on, then I will not touch anything around the hot parts. After all, we are working with mains voltage, so it's better to be safe than sorry. And speaking of voltage, let me show you something. This thing is quite power hungry. If we check a power meter which is attached to the circuit, we can see that the board without the heater on barely needs half a watt, and that is nothing. But when I turn on the heater and it goes at full power, the power consumption all of a sudden becomes more than 660 watts, so that is quite some power. Luckily, the TRIAC I picked has a maximum current of 8 amps, so this nearly 3 amps is not a big deal for it. Also, the heater is not always on. Both in free heating mode and reflow mode, it is switched on and off intermittently. So this is all about the hardware part that I wanted to show you. Now let me show you the updates regarding the coding. So here is the code, and since I have already showed this 2 years ago, I will not go into too much details, but I will take some time where there is some upgrade in the code. So we need just some libraries, such as the SPI library, and I use the Adafruit library to drive the display. And then I have to define the corresponding pins, and then create an object for the display. I use a rotary encoder, so I describe the corresponding pins to be able to handle it. And then I have a bunch of variables to take care of the rotary encoder and its button as well. Then I have some parameters for the thermocouple and the sensor module. So those are these parameters. And then I have even more parameters for example, switching the optocoupler, which then switches the TRIAC, and then also switching the fan. And then some status flags which tell whether the cooling fan is enabled, the heating is enabled, the reflow is enabled, and so on and so on. These are the parameters. And then I have a bunch of other parameters, and actually these are the reflow curve parts. And as I said, I copied these numbers from an existing graph which I had for the solder paste. So this is how it looks like. And then further down, I have some other variables. You can see that I have a target temperature, which is for the target temperature during the reflow. So basically these temperatures here. And then I have another target temperature here, which is the free target temperature, because that is for the free heating. And then I had to introduce some pixel factors, these guys here, for the X and Y axis. So if I calculate a time or temperature, then I can translate it to a pixel position on the display. And then these calculations do that thing. So here I also have a set of variables for those conversions. So this will help me to build up the reflow curve, which I draw on the display. And then since I have a quite complex menu, here are those parameters which are needed for the menu. So they take care of the position where I'm in the menu, which item is selected, and so on and so on. So it helps me to, for example, modify a parameter or select a parameter and so on. And then I have heater related parameters. So as I said, one of the features that I updated in this code is the proportional heater. So instead of an on-off heater, now I have a proportional heater. So basically I have a kind of a duty cycle which I adjust, and then that will determine whether the heater is on or off. And it seems to control the system better. And then I also, instead of using integers, I defined the reflow phases like this in an enum, and you can see how they are built. And then I already define a default phase. And then in the comments you can read some other parameters which help us again to handle the display. And then we arrive in the setup. So in the setup, yeah, I have to start the serial if I want to print something, but actually we can totally disregard the serial. I just used it for debugging. And then of course we have to initiate the pins for the rotary encoder. And then since one of the pins have to be used as an interrupt, I do that as well. So we are looking for a change here. And then we also read the current status of the CRK and DT pin on the rotary encoder. So then we can detect the changes as compared to the states which we have here saved. And then, yeah, a bunch of other pins, you can read them yourself. For the chip select, the TRIAC or optocoupler if we are very precise, and the fans or the pins which drive the transistor. And then I initialize the display here. So I just erase everything from the display, and then I print some welcome text, and then yeah, I do some self-advertisement and keep this wall text on the display for 5 seconds. And then I erase the display after the 5 seconds passed, and I draw the reflow curve by calling this function, and I turn off the fan because initially here I turned on. So while I'm showing something on the display for this 5 second, this part, then the fan is running, and that is just an indication that the circuit is working. So then in the loop, we have a bunch of functions. So it's kind of a state machine like thingy, but not exactly. So not super good implementation, but it works. So you can see that we measure the temperature, we check the button. So I'm just polling the rotary encoder's button. And then I update the highlighting on the display. I draw the reflow curve, and then any of these functions are called whenever a flag is set to true, which enables one of these functions to run. But they are like mutually exclusive, so you cannot run all the 3 functions at the same time. That would make no sense. And then the rotary encoder, it's a very long function. Actually, I haven't mentioned, but this code is more than 1,500 lines. So that's why I try to speed run through it, because if you are a supporter, you can obviously get this. So I just want to highlight here that you can support me by joining my YouTube membership, and then you can just download this code instead of listening to my rambling. So that might be easier for you. But then, of course, let's be honest, you have to open your wallet, because of course I put a lot of work in this and I'm not going to give this away for free. Either you invest your time by following my video and copying it, or you just buy me a pizza and then you can use it or modify it. It's up to you. The principles of the rotary encoder handling function is very simple. We check which menu item is selected, so that is this if, and we have several of those, so the if will evolve into else if, because again we have mutually exclusive states. But then yeah, we just use this very typical function which checks the status of the two rotary encoder pins, and based on their current state and previous state we either increase or decrease the selected variable. So I just show it in this example and the rest will be exactly the same. So what we have here is that we selected the preheat temperature menu item, and that means that we will be able to modify the preheat temperature when we rotate the rotary encoder. So we are entering here, so then this runs, and then based on the outcome we decide if we rotate it in, let's say, negative direction, we check if the preheat temperature is about 20 degrees. This line basically hinders you from going under 20 degrees. It won't do anything if the preheat temperature is 20 degrees and you rotate the rotary encoder further down. Then you can see that there is no else branch. So the only thing is that you are about 20 degrees, you can decrease the temperature, but not below. And then the else here is the else for the status of the pins. And then again, I kept the top temperature. So what I mean by capping it is that I don't allow the preheat temperature to go beyond 150 degrees. So as long as the value is below 150, you can increase the value, but when you reach that value, you cannot increase it anymore, at least in this situation, because you might not want to preheat your reflow plate more than this. But yeah, it's up to you. I also wrote it here, feel free to change it. So this is just like a guideline and you can learn from this. And then after this is performed, we indicate the code by changing this flag to true, that the menu is changed, and that basically means just that the number is updated. So we do that thing here, and when the loop here will want to update the highlighting, then it will update this new variable. And then we save the status of the TRIAC pin, so that storage of the state will allow us to detect a new change in the rotary encoder's position. And then we have the exact same thing, it's just with different numbers and different parameters, but it's the same. So this, I will skip it, I just let you to see it. So this is there if you want to copy manually. And then this is for the soaking temperature, soaking time, reflow temperature, and then of course we have a reflow time, and then cooling temperature, and then we have cooling time, and then we have a free heating selected. So again, we can go between 0, so this could be actually 20, room temperature. Of course, with a heater you cannot go below room temperature, so that doesn't make sense. And then 300 degrees. This is actually, it depends on the capacity or capabilities of your heating plate. So change it as you wish. And then we have a few non-functioning menu items, because if we are, for example, standing on the start or stop button and select it, we cannot turn the rotary encoder and do anything. So this is why I kept it like this, empty. Or also if we push the on-off button for the free heating, we don't expect any action to happen. So they are not implemented. And then finally the else is that that means that we are not actively selecting any menu item. So then we are navigating. So what happens here is that as long as this is above 0, then the item counter can be decreased. And once it would become 0, then the item counter goes back to 11, which is the highest value of it. And this is like when you scroll backwards on the menu, all of a sudden, after reaching the first item on the first page, you end up at the last item of the second page. And then this is the opposite of that. So as long as you are below 11, you can go forward. And when you would go forward when reaching 11, then the variable would roll over to 0. So that is when you are at the last item of the second page. When you click once more, then you would end up on the first page, first item. That belongs to item counter 0. Then I left this here accidentally, so I just remove it. This was also just for debugging. So how the reflow curve is drawn is actually the same as in my previous video. So I'm not going to explain it too much, but yeah, I erase the previous display, and then I draw the chart axis, and then based on those, let's say, parameters and pixel factors, I just calculate these variables, and then I draw the curve, which is hidden in another function, which I will show you later. And then I draw the values for the different portions of the curve. So you could see two numbers under each other at the different sections of the curve, and those are these numbers. So those are the pairs, which is the time and the corresponding temperature. So how long time we should spend at a certain temperature value. So we have the preheat, we have the soak, we have the reflow, and then the holding, and then after that it goes to cooling as well. And then on the first page we also have to print the start button, so that's there. And I set this redraw curve value to false, so we cannot draw it once again until we change the value of this flag to true. And then another function is the measure temperature function. As you can see, there is a relevant video for this. I have already made a video for this specific module, so I'm not going to go into too much detail. But as you can see, there's a timer here. Every 250 milliseconds, we read the temperature. And then how it's done is just by a simple SPI communication. So we just extract some data, 16 bits from the temperature module. And then we process that number by performing some bit shifting and then applying some calibration parameter or the resolution parameter. And then that is our TC Celsius. TC stands for thermocouple here. And then based on whether we are on the first page or on the second page, we print this variable somewhere. So because on both pages we want to print the actual temperature of the thermocouple, but I want to place it at a different place on the display. So that's why I selected the first page and the second page like this. And of course at the end we reset the timer, so this is basically, you cannot see any delay if you observe closely, because this is a non-blocking function. So we don't have a delay, we don't wait with a delay between two readings, but we just do a reading, and then in the rest of the time until another 250 milliseconds passes, we do something else. So that's that. And then the check rotary button, this is also a bit meticulous function, but it's relatively easy if I just explain one point here. So we are polling the value, as I said. So we check the status, and then if the rotary button value becomes 0, then we start a timer, and this is a poor man's debouncing. When the function is allowed to enter further down, then the rotary encoder's button will not detect any button presses for 1 second, and that is enough for the bouncing to decay, and that's very good. So then, based on the item counter, which is our position in the menu, we do something, and I wrote a switch case block for this, and I just show you the first block, and you will understand the rest. So we First of all, this means that we pressed the button on a certain or over a certain menu item. So for example, if the preheat menu item was highlighted and we press the button on it, we have to change its status to the opposite state. So for example, we highlighted it when it was not selected, then it is selected, that's why we clicked on it. So then I changed the status to it, to that by flipping it. And then we check what is the new status. And if the new status is selected, then we redraw the background behind the number, which is on the chart. So we want to indicate for the user that now this is selected. Or if it was selected and we want to exit that selection, we again press on the menu item, and that will, based on this line, flip the status from true to false. So we end up here, and what that does is that it resets its background to the default background, so it will not be selected. And then we also have to change the redraw curve to true, because when we deselect an item, that also means that we modified the value, so we have to redraw the curve. And then that happens with all these menu items. So for preheating, for soaking, again for soaking time, because we have temperature and time. So this is kind of a lot of things here, but as I told you, this is a very long code. So reflow temperature was the previous, reflow time, and then we have cooling temperature, cooling time, and then we have the start and stop button. So then what we do here, I might explain this a bit, that at the certain portions of the reflow curve, I printed the number and the time, and now I remove all of them by printing a black rectangle over them. And then I redraw the curve, and then I fill the background of the start button with a green text, and then I replace that text start to stop. So that will tell the user that, all right, now if I press again on that button, that will mean that I stop the reflow process. And then, yeah, I just set a few flags to their corresponding states. And here, this is what happens when we press the stop button. So the reflow is going, but now we want to stop it in the middle, let's say. Then again, we have to switch a few flags, and then we have to reprint the start button. So now we remove the stop text and we print start text instead. And then I have a separate menu item, of course, for the free heating, and that is also the same. So selection or deselection. And then we have a menu item for the free heating target temperature. So that is here. You can select it and then change the temperature, and then you can deselect it. And the same for that. So this is for the free heating button. So there is a heating button on the display, and this is the function part that handles it. This is how it looks like. And then of course we have the fan cooling as well. So that's quite simple so far. Again, we press the button, we have to change its color. That's what we do. We change it to green. If it is pressed again, then we change it to blue. So that's the default value. And then the update highlighting, again, these can be removed because that was just for me for debugging. We check if this flag was changed, and then we check which item has to be highlighted. And this is a bit tricky actually, because we have to be able to treat the transitions between pages. And that's why I have, for example, under case 0, an if else. Because if the previous counter was 11, that means that we are coming from the second page. So we were at the item number 11, and we further rotated the rotary encoder clockwise. So then the item counter rolled over to 0. And what we have to do is then we have to redraw the first page then. And that's what happens here. Otherwise, we came backwards. So the previous item was, 100% that it was 1. And then we turned the rotary encoder counterclockwise. So then the item counter became 0. And then we just have to highlight the selection, and that's all. So that's how it's done. And then yeah, the rest is the same. So again, if the item counter is 1, then we highlight, for example, the preheat time variables block, and then soaking time, and so on until we reach case 8. So again, we have to check, because this is the last item on the first page. If the previous item was 9, that means that we were on the first item of the second page, and we turned the rotor encoder backwards. So then again, there is a transition from page 2 to page 1, and we have to treat it. But otherwise, we just have to do this, because we come from the 7th item. And then again, on item 9, that means that we are at the first item of the second page. We have to redraw the second page, or not redraw, but draw it. So that's what we do here, and then we print a few things. Otherwise, we are already on the second page. So for example, we were on item number 10, as I wrote it here, and we turned the rotor encoder backwards. So then we don't need to redraw the page, but we just have to update the selection. And page 10, it's the middle item or center item of the second page, so we don't need to do anything fancy. We just draw a selection or highlighting rectangle around the button. Here we again have to handle things, because it can also happen that we came from the first page, first item, and we navigated backwards. So then we ended up on the last item of the second page. And this is how we handle it. And of course, we need to know what was the previous item. So we always take care of it. And then we have to deselect the things, because imagine that you are jumping from item 1 to item 2. So it's not enough that you now highlight item 2, but you have to remove the highlighting from item 1. And actually that is handled in these functions. So based on the previous item counter, we check each cases, and then we remove the previous items highlighting. So that's how it's done. So item 2 to item 6, and then item 7 down to item 11. So, and then of course we change this flag to false. So we will wait for another trigger from another part of the code. And then here comes the probably more interesting part. So this is the heating, and this is not for the free heating, but this is for the heating which is supposed to follow the reflow curve. So this is a bit tricky, because based on your heater, you might have different responses. So your system might not behave as you would expect. And therefore, the real temperature will not follow the reflow curve that you drew. So that's more like a guideline. So if we are allowed to do reflow, and if the heating is enabled, then we can enter below. And what we do here is just we run a timer, and actually now it's not 1 second update frequency, but I run it 250 milliseconds because of the proportional control. So what I do here is that I print the real-time curve over the reflow curve with these things. I just call this measure temp px and measure time px, and I calculate them based on the actual temperature and the heating time. So I just convert these two values into the pixel values. And then I also print the elapsed time at the top part of the display, just so we see how we progress. And then I call this function twice, and you can see that they are the same, but I have an offset of 1 pixel on the x-axis. So this is basically printing a fake thicker line. So this is the original measurement, but 1 pixel wide graph would look a bit funny. So I just print one more with a little offset, and then I have a thicker graph, which looks better. And then during heating, we have different phases, and then we have to check which phase we are at. And of course, we started the preheat. And then, based on the elapsed time, here we calculate the expected temperature. And this is purely based on the graph that you draw in the beginning, the reflow curve. And then this target temperature is printed by a function. And then we checked what is the reflow state. And then this control TRIAC tries to control the heating plate. And then here, there's a function which lets the program to advance to the next step if the temperature reached the preheat temperature that we prescribed and elapsed time is larger than the prescribed preheat time. And then the same strategy is applied for the soak. So you can see the wall soak here. And then the same for the reflow. And then the same for the hold. And then slightly different for the cooling. So the cooling, what it does is that we remove the target temperature because it's not applicable anymore. And we erase the text as well. And then we print cooling on the display. And then I turn off the heating first by changing the flag. And just to be sure, I set the TRIAC pin to low here manually. So this turns off the optocoupler, which turns off the TRIAC. And then at this part of the function, I change the flag, which enables the cooling. And I turn on the fan and basically start the timer for the fan. And yeah, this is just a elapsed time counter. So basically this is the seconds in this parenthesis, just to see the elapsed time on the display. So since we changed this part, if I jump back here, the if won't be true anymore. So we have to go down, and then in the rest of the time, because still the reflow is true, but it's just that the heating is not true, the else will be performed. So then again we check the elapsed time, and then for 2 minutes we let the cooling fan run. And after 2 minutes we turn off the fan, disable the cooling and disable the reflow process. And then I redraw the start button and redraw the wall curve so a new reflow can be started. And otherwise here, if the cooling fan is enabled, which is like happening before this will be like performed, then I keep counting or keep tracking the time, keep drawing the chart, and then keep printing text on the display. Actually what happens is that the millis gets larger and larger, but this timer was started right here. So we just noted down the value here at that moment, and then we keep reading the millis. And then after a while the difference between these two will be more than this value, and then we know that okay, 2 minutes elapsed since I turned on the fan, and then I can exit the wall function. So then it's done. So then how the free heating works is that the reflow must be false. So I cannot have a reflow process plus the free heating at the same time. That's what I said in the beginning, that they are mutually exclusive. So if the free heating is enabled as well, then I calculate the error, which is the difference between my target temperature and my measured temperature. And I calculate the so-called duty cycle, which is kind of the same as a duty cycle for the PWM signal, because here I keep the TRIAC on and off for a certain period of time. And then I calculate the elapsed time by fetching the current time in millis, and then I do this modulo, so it gives back me the remaining part. And that remaining part is the elapsed time in our case. So you can see some examples how it's being calculated. And that number is used to compare inside this if condition. So if the elapsed time is less than this, which we can consider as, let's say, heating power or some kind of parameter like that, then we turn on the TRIAC. Otherwise we turn it off. And this will basically cycle the TRIAC on and off and allow us to periodically turn it on and off. But instead of doing a on-off regulation, we do a more intelligent approach, and we base our on-off period on the distance from the set temperature and the proportional parameter Kp. So if your system doesn't behave as you want, you have to modify this Kp value. And then with this timer, what I do is that every X amount of time, I check what is the duty cycle, and then this is basically an if condition here. So if the duty cycle is larger than 0, so that is this condition, then I print a red background behind the target text on the display. And that will actually mean that the heating is on. And if the background would become blue, that means that the heating is off. That's simple. And then I just, to be safe, I disable the TRIAC pin whenever I don't need it. And then the free cooling is super simple. So that is that when we are not in a reflow mode, then if we change the status to true, we turn on the fan pin or we turn off the fan pin. So that's that. And this is just a really simple way of printing the lines and the chart. So this is how it looks like. This is what you can see here. And then we have the free heating page, which is the page number 2. So I erase the display, and then I have to print some text on it and another text because I have the measured temperature on the top, but then I also have the target temperature below it. And then I have 2 buttons which are drawn with these 2 lines. And then again, I do some self-advertisement because I have some space on the bottom of the display, so I just put my website there. By the way, I highly recommend you to visit my website because it's full of information, and I wrote an article related to this code and device, and that might be useful for you. Oh yeah, and I made a separate function for printing the target temperature. This is the target temperature which is printed during the reflow process. So as I said, the target temperature is calculated by the parameters on the reflow curve and the elapsed time. And based on that, we have this target temperature, and that is printed. So we can see where is our set temperature as a function of time, and where is our real temperature on the hot plate. I have this function which I mentioned earlier. So what this does is, again, very simple stuff. It checks the difference between the current temperature and the target temperature, or more like it checks their relationship. And if the temperature measured on the plate is lower than the target temperature, then I set it to green. And that indicates that we are approaching the target temperature. And if the background would, for some reason, become red, it would mean that we have an overshoot. So we are actually beyond the target temperature. And then the red indicator will tell the user that something is wrong. And then right below is the function which helps these 2 lines to print the text to the place where they should go. And then finally, I have this control TRIAC function. And this is the same strategy as we have where we have it right here for the free heating. But this controls the proportional control for the reflow process. I did not want to mix them, so I just broke it out into 2 functions, and this is the other function. And then, since for the free heating we are not really restricted by time, I have another KP value. Here I manually defined the KP value because the reflow curve has a certain time constraint, so you have to be at the soaking temperature after a certain amount of time, and you have to stay there for a certain amount of time. So therefore, you might need a different response, faster response, than you have or want to have during the free heating. So then I just put it here manually, but otherwise the same. So we check the elapsed time and how it is related to the period, which is here now 250 milliseconds. And then based on this relationship, I turn on the TRIAC or turn off the TRIAC. So it's that simple. And actually this is the end of the code. You can see this is 1481 lines. So it's a very long code and quite complex, but it works. So far so good. So I'm happy with it. But if you have any ideas or suggestions, please leave a comment. I will read it and respond to it. So don't be shy. And with that, I think I finished the video here. So once again, don't forget to visit my website. Link is in the description. I wrote a detailed article about this thing, and you can see all the resources and everything. Especially if you are my supporter, then you can get this source code very easily. And also don't forget to visit my PCBWay project site and PCBWay's website, because you can also find further resources there, or you can even participate in their ongoing challenge. So I hope this video was useful to you. I hope you learned something, and see you in the next video.